All right, let's look at another problem. This is an access door held by a chain that has a force of 100 newtons developed in it, held in place at the angle 30 degrees. Axis XYZ is given. First of all, this 100 Newton expressed as a force vector, but also wants to find its projection along direction CD, which is kind of diagonal of this axis door. So this is the direction we want to find the projection of that AB force AB along this axis. All right, so let's just start. Let's make this a little bit smaller, a little bit more manageable. So first thing first, for part A, let me see what I need to do. I need to find tension AB as a vector. So what I do is use unit vector. So magnitude of AB next to unit vector AB. Magnitude AB, position vector AB over magnitude of position vector AB. I know this one is 100 newtons. It's given. So all I need to do is find unit vector of AB, which is position vector AB divided by magnitude of position vector, and that gives me this force vector, or in vector format. All right. I always like to do a quick table so I can keep track of my points and coordinates and all of that. I write X, Y, Z, and then units. All right. So if I put C at 0, 0, 0, then let's start from top. So A, I have to look how much it's moved on x-axis, which is 0, how much it's moved on y-axis, which is located like this. So Z, Y, this is 900 millimeters, point A at an angle 30. So in Y, it has moved 900 cosine of 30. In the Z direction, it has moved 900 sine 30. Okay. Point B is on x-axis. It has gone back. So this is positive x, this is negative x. It's gone back 1200 millimeters. In y-axis, it hasn't moved on y-axis at all. It's still at 0. And in Z, it has gone up 900. Okay. Last thing I need to do, I'm going to use it later, is point D. Kind of like A, similar to A. The difference is it's a little bit further back. So it's minus 1200. And if you do the math, 900 cosine 30 is going to be 779. Z 900 sine 30 would be 450. Okay, I think I'm good. Another way to do these, also you can write them as meters. Doesn't make a difference. This will be 1.2, this one will be 0.9, 1.2, 779, 450. Same thing, 779 and 450. These are meters. Okay, I'm going to use meters in my calculation. All right, position vector AB, R, AB. I'm going from A to B, so I'll start with B and deduct coordinates of A from that. which will result in 1.2i 779j 450k meters. I also need magnitude of RAB. Magnitude of any vector will be 1.2 squared, 779 squared, 450 squared. These are all meters squared. This will result in 1.5. All right, I think I'm ready to go back in my initial equation and substitute everything. So tension in AB as a vector equals 100 newtons, and then this position vector that I just found divided by its magnitude. So when you divide a vector by magnitude, that means I get divided by 1.5, J get divided by 1.5, and K get divided by 1.5. So minus 1.2 divided by 1.5 meters, and that's I. Minus 779, that's J, and that's meters, divided by 1.5 meters. Sorry, running out of space a little bit. Plus 450 divided by 1.5 meters, and that is K. So 100 newtons get multiplied by the first term, 100 newtons get multiplied by the second term, and 100 newtons get multiplied by third term. If you do the math, you should get minus 80I minus 52J plus 30K, and that is in Newton. So that is for part A. Express this force as a force vector. We did it. All right, part B says, find projection of this force along CD. In order to find projection of any force along any direction, you have to dot product that force by the unit vector of that direction. That means in order to find projection of tension AB along direction CD, I have to dot product the vector I just found in part A by unit vector of that direction. Dot product. Okay. One thing to pay attention here, you see this one doesn't have an arrow because this is a scalar. A vector dot vector results in a scalar. Okay, I have a lecture on this one. Please watch the lecture if you want to know why and how, but this is how we do it. So that means I have to find position vector CD and then divide it by magnitude of position vector CD, and then I'm all good on the dot product. Look back at the table from last page. RCD going from C to D, you got to deduct components of C from D, will result in minus 1.2I 779J 45K, and the units are meters. Position vector, or sorry, magnitude of CD, sum of the squares and then the square root of that will be again 1.5 meters. So unit vector of CD is just I divided by 1.5, J divided by 1.5, and 4.5 divided by 1.5. So 1.2 over 1.5 I. 779 divided by 1.5 J. 45 divided by 1.5, and that is K. Alright, dot product. Dot product of two vectors, you do the x components together, y components together, and z components together. What do I mean by that? Is, let me write it clean here. So T A B dot unit vector of CD is minus 80I minus 52J plus 30K dot the unit vector that we just found, and that one doesn't have any units because it's meters over meters and they cancel each other out. So in order to do dot product, you multiply this by this. Forget about the i's, j's, k's. So it's going to be minus 80 multiplied by, and that's 0.8. Then you do these two together, minus 52 multiplied by 519. And then finally you do these two together. So x by x, y by y, and z by z. And that will be 30 multiplied by 0.3. And this is newtons by nothing, newtons by nothing, and newtons by nothing. So the result in newtons. You see there's no ijk anywhere. There's no ijk anywhere. So if you do the math on this one, you should get 46 newtons. And this is a scalar. This is a projection. This is a component of this tension that we had, that we found, tension AB, along direction CD. You can, for practice, find it along, find projection of the same force along AD, and then find projection along CA. Totally random, those two random directions, just for practice. So you got a dot product, the same vector by unit vector of AD, dot product, same vector by unit vector of CA. I hope this was helpful. Thank you very much.